Right. So we start the optimization methods content here. So first, let's discuss the, sorry, no. Resume, all right. So here we are. So firstly, we will go through a brief introduction and have some examples. This tells you roughly what the optimization methods is about, what we are going to talk about, the classification of optimization problems, and you know, the ideas of what it means that something is optimized in terms of mathematics. After we've had this brief introduction, we will talk about certain mathematical concepts that are crucial to the understanding and solving of optimization problems. And one of the key issues here that we deal with is called convexity. Convexity is a property of functions and property of sets that has an immense help. You know, if a function or a set that we are discussing is convex, then this is immensely helpful in solving optimization problems, and there's several methods by which we solve them work perfectly when we have convex sets, convex functions, and we'll discuss things like approximation using convex functions and convex sets at the end of this course. Then we talk about what is called linear optimization, a very powerful subclass, but also in some sense very limited subclass of functions and problems, namely linear. And linear optimization is often the go-to optimization problem class, and the methods thereby are the go-to methods of most optimization that works for more general settings. I'll discuss some of that also, but I'm assuming a certain familiarity with matrix algebra, because linear optimization really isn't, you cannot really tackle it if you don't understand how matrices work, like matrix multiplication and stuff like this. Not going to talk about the interior point methods and so forth all that much. I'm going to mention them a little bit and the ideas in them. So much of this material works in the way that I give a problem class, like in the case of linear optimization. I give one method for solving it in more detail. Then maybe another one we discuss a little bit on how it differs from the first one, and then we may mention others as well and their basics of how they function. But the focus is usually on one method of optimization, and in this, particularly in this linear optimization system. Then we talk about unconstrained optimization. You'll understand what that is shortly. Some of the more common methods, like the gradient method, Newton method, modified Newton method, and so forth. Then we talk about constrained optimizations, situations where there are equality constraints, inequality constraints, and so forth. It's not mentioned in this table of content, but one of the key issues there is what is called the KKT, the Karush-Kuhn-Tucker conditions, which guarantee don't guarantee optimality, but which are necessary conditions for optimality. So you have to understand the difference between necessary and sufficient conditions. Usually we cannot give sufficient conditions for optimality in general, but we can give necessary conditions in certain situations. We'll discuss that as well. So the mathematics of this is mostly going to be of continuous problems. So not that much discrete problems. We can discuss discrete problems in the exercises, and definitely your project work can contain discrete optimization problems, but the theory of this course will mostly be focused on continuous optimization problems. A supplementary material, which seems it's given here as appendices, but the thing is we will be covering some of these things, and I'm going to be assuming a certain level of knowledge in these issues. So if you are not familiar with vector and matrix algebra and vector analysis, I really do suggest that you brush up on that by reading this Appendix A. We're going to take a little bit of an abstract view on mathematics here, because I am a firm believer in the idea that this abstract thinking is very good way to approach all problems, so that you think it at the highest possible level first, and then bring it down to a more concrete manifestation of the problem until at such time as you have a concrete method for solving it. But you start by analyzing it at the higher, more abstract level. I'll explain shortly what that means and how we go about it. And then there's Appendix B, which is about differential calculus. Some of these derivatives, we're going to be needing to talk about the derivative of a function when that function is more general than just real to real function. So we're going to be talking about, there's a vector space, and then there's a mapping or a function from vectors to real numbers. And then we need to be talking about the different kind of derivatives of that. And that's something that we need to discuss. Also, mean value theorems, the concept of second derivative, derivative, the first order derivative, the second order derivative, and then optimality criteria. We'll discuss those. But what we will do is this appendices A and B, we will go through them as a detour kind of sometimes. So we are mostly going through these chapters 1 to 5. But then whenever we encounter material that says, okay, here, in order to understand this concept, we need something from the appendices. So I'm going to go through the appendices a little bit. And if that is vague or unfamiliar to you, then you should read that appendix on your own and try to figure out how that thing works. And of course, asking questions is perfectly fine. At all times, you are allowed to ask questions if you feel you don't fully understand. All right, so let's get to the material beginning. So firstly, there's the introduction. So in optimization, the goal is finding the minimum, sometimes maximum, but it doesn't really matter which, because we can, with an easy mathematical trick, we can turn a minimum into a maximum, or a minimization problem into a maximization problem. Just a second, I'll make that background light a little bit less prominent. So let's say that we have a function from some set x to the real numbers. And this x can be some kind of vector space. It can be very general. It can contain functions. It can contain any mathematical objects, basically, as long as each of those objects is given a real number and by this function f. And then we have some subset, which is the omega meaning the feasible set. These are the ones that we could even consider in theory, and find the one that minimizes f of x. So let me give an example. Let x be, for instance, all the possible driving routes from your home to the university, and you need to find the fastest way of getting to the university. So this f of x is now some route. You go through there, you go through there, you go through another route. I mean, you look at the map or something like this, and then you want to find the route that has the shortest time that it takes to travel from where you are coming to, let's say, the university campus. And this would be your f of x, it's the time that it takes to travel through the route, and x is now some, you know, path on the map or something, however you define that. And then this feasible set, this omega, may be something like, okay, let's say that you are driving, and these x's are the ones, the routes that you can drive. And then the feasible set, this omega, would be the set of all roads. You know, you're traveling via road such that you're not driving, you know, on the wrong way on a one-way street, for example. You're not driving through someone's lawn and something like this. So you're not, it's not unconstrained, meaning you can just drive on a straight line from here to there, you know. Instead, you have to, you know, respect the, let's say, the traffic laws. So that means that not all possible routes are there for you to take. That means X being all possible routes. Instead, you have to take some, well, I wouldn't call it a detour, but you have to take some indirect route, in the sense that, you know, you have to go use roads, and you cannot turn left if turning left is forbidden, and so forth. So this function that associates with each of your objects that you are considering, the function that associates a value or a cost, is usually framed as a cost, meaning that you want to minimize it because you want to pay as little as possible. In this case, you want to spend as little time getting from here to there as possible. So your optimization, your minimization, you want your minimum cost to get there. And this feasible set, it's feasible in the sense that feasible meaning, you know, something that can be done. You know, unless you have a tank or a, you know, something like this, you know, you can't just drive through buildings and things like this. So you get what I mean. And then the goal is to find an object in the feasible set that minimizes the objective function or the cost function, the minimum cost point. And we say that this X star is the global optimum to this problem, and f of X star is the optimal value. So remember, the optimal solution is the point, and then the optimal value is the value you get. So it says here, this notation, X star is the argmin. Argmin means that the minimum argument, the X that makes this the smallest. You see here? Sorry, I'm going to use the annotation. So here. So this argmin here means that this X is the smallest argument of the function f. Is such an argument of f of X that it makes this f of X the smallest in this set omega. And this min, if without this arg, the min is the optimal value. So this is the optimal solution, and then the optimal value is just that when you don't have this arg in there, right? If you have a problem where you need to find the maximum of some function, you can easily transform it into a minimization problem. Minimization problem by just changing the signs. So maximizing f of X, then minimize minus f of X and put a minus in front of it afterwards, right? And then you have the maximization problem. So, you know, minimization and maximization are not mathematically different enough to warrant a different treatment. So we are just going to assume that we're always talking about minimization problems. Well, okay, this seems easy enough, but more often than not, it is possible. Not necessarily in my example of driving routes, but in some cases it is possible, it can happen that the function that we are talking about, this f of x, can attain arbitrarily small or large values on when we are inside this set. In that case, the problem doesn't have a finite solution. Instead, it can be minus infinity or maximum can be infinity. One example would be such that, I'll write it in the chat window, you know, minimize 1 over x, x is greater than 0, right? You want to find the, sorry. It should be x is smaller than 0. That was, I miswrote that. Sorry, you minimize 1 over x where x is smaller than 0, all right? So as x approaches 0, but it's negative, then this goes towards minus infinity. And you can always inch a little bit closer towards 0 and make this smaller. So when we write infinity like this, minus infinity here, doesn't mean that there is a point at which something is infinite. It just means that you can make it smaller by going in some direction indefinitely. So we don't need to deal with infinities here as such. We're using infinite to use, using this infinite symbol to discuss or to point out to a situation where we cannot set an upper limit. So it's unbounded. Unbounded and infinite in some sense in this situation can be thought of as the same thing. It's not the same thing, but we can pretend that it's the same thing here. Usually in this course, our feasible set is some vector space. So X, our not feasible set, but our space of possible solutions is some vector space, which is usually R to the n, so n-dimensional vectors. And then some subset thereof. And the subset is often given by use of some functions. So there will be constraints. So you have vectors for which some h of x is 0, and then some g of x is smaller than or equal to 0. So the problem can be written in a format where we are minimizing a function where x is a real valued vector, such that it has some set of equality constraints, I equal from 1 to r, hi of x is 0. So this would be just, you know, I'll give an example. So minimum, let's say my x is r2. So this means so it's like x and y, x's and y's. So minimize f x y, and then subject to, and then we can have like this. Let's say take one h constraint. It would be like x plus y squared equal 1. Sorry, but because it's written as 0, so we can write this as x plus y squared minus 1 equal 0, right? And let's take a g condition, which is smaller than, let's say that x squared plus y squared is smaller than 9. But then, you know, we want this to be in that format, so we can, it should be smaller than or equal to, sorry, I wrote that. So I'll write it like this: x squared plus y squared minus 9 is, I'll write it like this: smaller than or equal to 0. Sorry, I first wrote smaller than, but it's smaller than or equal. Well, one question here that comes to mind: why does it matter whether it's smaller than or equal to? Well, one of the things is that if you, I'm not sure about this one. This was just I drew this from the top of my head, so I cannot say whether this is such a problem. But there are several problems where, you know, if you have smaller than, but not smaller than or equal to, then you can't really minimize it. Let me just give an example. So minimize minus x subject to x is smaller than 5. So if we try to minimize this x, minus x, well, it's minus x, so it's minimized by making x as large as possible. And x must be smaller than 5. But now this doesn't have... Oh, that's true, by the way. Okay. Okay, it says here that if I use the chat board as writing board for the problem, the chat will not show in the recording. That's actually true. That is a good point. So let me just do something else. I'll do something else. I'll use something else here. So, okay, I'm going to fix that for the next lecture then. I'm going to fix that for the next lecture. I'm not going to just use time here to fix that. Well, okay, let's have a 5-minute break. 5-minute break. I'll figure out a different way of doing this. Just a second. Resume recording. All right. Oh, that's the problem with this, is that this thing doesn't. I'd like to say that this doesn't obey my commands. Yeah, that's really frustrating, because this is now the... All right. Now, let's go here. So like I was saying, you know, no, man, this is really frustrating. So like I was saying, these equality and inequality constraints need to have that equal to thing. And we'll explain that mathematically why that is shortly, but just a quick example of how it works is that, for instance, if we are minimizing minus x subject to x smaller than 5, then in this case, we cannot find the maximum of x, which is the minimum of minus x, in this set, because as we get closer and closer to 5, we can get bigger and bigger values, 4.9, 4.999, and 4. So forth. And this is not going to have the maximum, which clearly would be 5. We can get closer and closer to 5, but not actually to the 0.5. X is equal 5. So that's why this doesn't have a solution. So more often than not, we want these inequality constraints to be such that there is an equality. So we can actually hit that point at the edge. I will formalize this intuition later in better ways, but for now, the idea is this. So depending on the nature of how this f of x is defined and how this feasible set is defined, we get different types of optimization problems. So here's the classification that is the most important thing. If we don't have a feasible set characterization where there are any constraints, it's just, you know, it's this space, the set of real numbers, then we say that that's an unconstrained, or what we call a free problem. Meaning that there are no constraints. There is nothing that like x needs to be y plus 1 and then find x and y such that there's nothing like that. It's a free problem. There's no constraint to be considered. Then all the problems all the hardness or all the complications of solving such a problem come from the objective function itself. No constraints, just the function, and the function may be easy or may be complicated, but we need to find the minimum of that. Example of such a problem might be, let's say, minimize x x squared plus 5x minus 2. X is real. All right. So find a real number such that this is minimized. Well, I hope that you can solve this because I'm assuming certain familiarity with functions. But if we want to solve this, there's several different ways of solving it. From high school level mathematics, we can find, for instance, we find the derivative of that. So it is f of x is equal to x squared plus 5x minus 2. Then f prime of x is equal to 2x plus 5. And then we set this to 0. Then we get that x is minus 5 over 2. So, we find that the minimum of this, well, we can do stuff to verify that this is so, but if you are familiar with how this works, you will find that that's the minimum, that it's going to be a parabola, and then the bottom of the parabola will be that minus 5 over 2. This x, whether it's continuous, if we have x is consists of real valued, real vector space Rn. It could be integer problem, meaning that it's vector, but its components need to be integers. It could be what is called a mixed integer problem. All these vector components, some of them are real numbers, some of them are integers. So let me give some examples of these. A continuous problem, fairly easily characterized. Most physical problems where you need to find the position of something, what is the perihelion of some orbital motion, I'm just thinking whether perihelion was the closest point. I'm now closest point to the sun. I'm not now sure which one it was. It's been time since I've researched orbital mechanics. If there's something continuous variables, usually when you have something like you have let's say you have a electrical circuit and you want to find the current and the voltage that minimize certain quantity, then those might be real values. It can be negative or positive depending on which direction it goes. Integer values, very often things like you need to pack you're robbing let's say you are in the middle of the night, you've broken into a department store and you're robbing it, and you want to get away with as valuable loot as possible. So you have all these boxes that have different kind of material in them, TVs, computers, and things like this. And you're the brains of the operation, so you need to figure out how to maximize your loot. So how many TV sets, how many computers, how many cell phones are you going to be putting into your van before the police arrive? So that would be an integer problem. How many? Positive integers roughly. Okay, it could be negative as well. Let's say you're leaving something also behind, not sure. Okay, this is weird. Mixed integer, some problems you have continuous variables and you have integer variables. You have to turn these knobs, their values are real numbers, and then you have to flip these switches, they're integers, or put this into, put the kettle on 6 and wait for this many seconds and something like this. So in the same optimization problem, you may have both real numbers and integers. Also, a discrete or binary problem is usually framed as a way that problem is, it's on and off. Something is there or isn't there, a binary problem. zeros and ones. You know, you pick something or you don't pick it, and you have n things to choose from, and each one is either in or out. A very common class of problem. Most of this course will deal with the continuous problems. I mean, much or if not most if not even all, almost all of this material deals with continuous problems. We've been trying to get, there used to be a course, another optimization course, which dealt with integer and mixed integer and binary problems. That was canceled, and you know, one course of 7 weeks, I don't think it makes sense to discuss all kinds of classes in one course. So I'm going to focus on this continuous problems on this course, mainly because the material is so good. This is the type of X, how it goes. Then there is this one classification, is the optimization problem linear or not? So linear optimization, in fact, is affine. Why is it affine? So, well, linear is actually a misnomer. Affine meaning, you know, it's of the form ax plus b, where a and b are constants. So your functions, or, you know, maybe this is x could be vector. X could be vector, but you know, a and b are constants. So your constraints and objective functions are all expressible in terms of this ax plus b and sums thereof. And then there's nonlinear optimization. Or nonlinear optimization happens when some of these functions are nonlinear. And then those nonlinear optimizations fall into different categories like convex, quadratic, geometric, so forth. We'll discuss these issues a little bit. So most of this course, we deal with continuous problems that are either linear or convex. And then there are some situations where they are non-convex, and we'll discuss that non-convexity problems there. Quadratic problems, well, quadratic problems are convex. Quadratic problems are problems that can be expressed, and I'll write it here in this window, as it can be expressed as x transpose A times x plus B transpose times x plus C equals 0. So this is very often the case where you have a matrix A, you have a vector B, and you have a constant C, and then you can express it with this. So this is just a real number which is equal to 0, but this is quadratic, you know, in the sense that there's a second, you know, powers of 2, or, you know, cross reference the multiples of different components of the vector x. So we'll talk about that. One concept we said earlier, and I'll just show here, we said the global optimum was an optimum in that x star, whereas the optimal value, it minimizes the objective function over the whole set. So nothing in this set omega gives a smaller value to this f of x as this x star. Then we say that it's a global optimum. So among all the possible points in the set omega, none are smaller than this x star. That's global. But then another issue is the concept of local optimum. A local optimum means that there is some region, you know, around this point x0. So the x0 is, let's say it's here, and then around it there is like this some kind of sphere or ball. It's a sphere open ball, meaning that there is some region around that point such that this x0 is the global optimum to a problem where you just consider that point, you know, the ball, the tiny sphere around that region. So let me annotate. Let's see if I can annotate this. So let's say, so here's my whole omega, right? Here's my omega. that's my x0, and this is the b, right? So I'm now saying that this point here is a local optimum if inside this sphere here, you know, or this ball here, this point at the middle here, and just draw it as tiny x here. That point is the minimum inside here. There may be another one here that is even smaller than that. So this is not a global optimum because in this whole set, I can find a better point here. But inside this tiny region here, that's the optimum. Then we say that it's a local minimum. And local minima are a bit of a problem because in some situations we can find locally a point such that it looks like it's the best. But then somewhere else, there is a point that is even better. So we get to that problematics also. So here's some examples. Here's an example of a fourth degree polynomial. This fourth degree polynomial, x minus y plus 2x squared plus so forth and so forth. We have to find the minimum of this. It's a nonlinear, unconstrained optimization problem. It's not easy to solve, actually, this. We can try to solve this by hand, and I'm just not going to do that now. I'll show you towards the end of this course, I'll show you it's relatively easy. We can do it with software and MATLAB and so forth. And one thing I want to say about this course is that you know, solving a problem like this by hand, you know, to quote an internet meme I once saw, ain't nobody got time for that. So we can use software to solve this problem, or at least parts of this problem, to find something that makes it makes it a little bit more tolerable. So before we end today, I'm going to show a little bit of how we can do this. Then this is, but let's look at this, what this problem is about. It's non-linear because obviously there are other, it's not just some constant times x and constant times y and then additions of thereof. So it's non-linear. There are no constraints. It's the whole R2 is the, all real values are feasible. And yeah, not going to mention about whether it's convex or anything. We can discuss that shortly when we get there. But it's an unconstrained nonlinear optimization problem. There's another problem. Let's say that they're subject to constraints. So we have this function minus x squared minus y minus 2 squared plus 7, x and y being real numbers, and the constraints are minus x to the 3 plus y squared plus x minus y smaller than or equal to 1, and so forth. This is a nonlinear constraint optimization problem. It's got constraints and it's nonlinear. All the constraints are actually also nonlinear. One more example. Let's say we have a function that maps real numbers, you know, real vectors to vectors. So it's not a vector to real number, it's vector to vector. And we have some point in that, in the range of this function, so in Rn. One way to solve an equation, f of x equals b. So if we want to find f of x equal to b, we can actually transform the equation solution, solving the equation, we can actually transform it into a minimization problem. So we can minimize the squared norm, or, you know, even the norm without the square, but let's say the squared norm of the residual. So fx minus, minus b, we minimize the norm of that, and it turns into an optimization problem. So you know, most of the mathematical problems that you will encounter, which mandate you to solve a problem, can in fact be expressed as optimization problems. So optimization, I once had the privilege of knowing the late Anatoly Putkovsky, who was a famous, I'm not sure that famous, but we knew him, and I knew of him before I knew him. A Russian mathematician who specialized in control theory. And once I told him that I would be doing my master's thesis in optimization, he said, well, that's great, because optimization is the biggest discipline in mathematics, because everything can be transformed into optimization. So the thing is, the problem with this is, if you have this minimization problem of fx minus b, and take the norm of that, depending on what this f of x looks like, this objective function may have these nooks and crannies, you know, it can look like very weird, so that there are local minima, meaning that this in several points, it looks like, you know, if you move even a little bit to any direction from this, it stays, it's going to get bigger. So it looks like this is the minimum. But unless it's actually zero there, then it's not necessarily the global minimum. And it can be really difficult to find where this global minimum is. And this results in a situation that we may find an x that makes this f of x minus b very, very small. You know, like, you know, very, very, very small. Something like, if you use computers, you get something like, you know, very close to the minimum number of that you can actually express. But the solution may be really, really inaccurate, so that, you know, your x may be really far away from your actual optimum, even though it exists. And this is something that you need to understand. And this is something that, especially those who work in machine learning. And just as a quick, I'm assuming many of you are actually working in machine learning, because in the recent years, it's been a very popular topic, and many people who come to take this optimization course realize that, you know, when they're doing machine learning, they're actually very often minimizing residuals like this. And, you know, the error, you know, they have a classification problem. You know, your function f tries to identify, you know, the function, but let's say your neural network tries to identify a certain thing, you know, as a cat, you know, something like this. Let's say it tries to identify a cat. And then, you know, you have your error function, which says, how far off am I? I'm trying to predict this, you know, how far am I from actually thinking that this is a cat? And then, you know, you get the residual, okay, this is not far away from being a cat, but well, actually what you are looking for is an elephant, right? So the residual being small doesn't mean necessarily that the error in the codomain is small, right? So if you're going to the error in the domain, in the codomain, meaning that the place where you are looking at, f of x, is not far away from b. But x may be very far away from what would be the x that goes to b, right? So this is a word of warning that needs to be understood if you are applying these optimization methods. And it's in all mathematical models, so of course a risk. I just wanted to make you sure you understand this. So this is more like a disclaimer, or a, you know, how should I say, get out of jail free card. So if you're using these methods to solve your problems, then it's not my fault if you go wrong. And I'm kidding here. Well, it's not my problem, but, you know, that's not why I'm saying it. And the thing is, this can even happen with linear equations. For instance, If you try to solve a linear equation AX equal B with Gaussian elimination, we're not going to do Gaussian elimination here, but if you do the Gaussian elimination, then what happens is, even if you get, if this is, let's say this is not a full range problem, meaning not a full dimensional problem, meaning that this is, A is, for instance, it's singular, or it's flat, or something like this, and you try to solve this using Gaussian elimination, you will get a small residual, meaning you get an X where AX minus B is actually small, but the X may be really far away from an actual X that makes this true. Well, worse, it may be very far from the smallest X, with the X with the smallest residual, even if the residual looks very small, if it doesn't have a unique solution, well, if it doesn't have a solution. Just a word of warning that even though you can frame these equality or approximation problems as optimization problems, then nothing guarantees the accuracy per se. You have to analyze it separately. Okay, so the first for the first week's problem, for the first session's problem, one that you might want to discuss or think about is proving the identity 1.2, which is stated here. The maximum and the minus of the minus is the minimum. Not going to go through that here. Today, I'm going to cut this lesson short because we will continue tomorrow, and we'll continue tomorrow on convex sets and functions. This is more like a warm-up and basic laydown of the ideas. Just so, but not going to end this session quite yet. I'm going to just very quickly show you a small example of how. I'm going to stop the recording. A very quick introduction. So I hope you have access to MATLAB. So some of the things that we might do, there's the minimization of this f of x equals something like this. So I'm going to just write symbols x, x, y. Oh, what? It seems I don't have the necessary toolbox at my disposal here. Oh, that's really not. Yeah, that's not going to be working very well. Damn. Okay, I have to install the toolboxes before I get there. So the student lab MATLAB has the symbolic math toolbox, but it seems that my desktop, my laptop version doesn't have it, which is too bad. Yeah, so I can't demonstrate it to you with this computer. I'll have to do this from my office. That's too bad, but I'll do it from there. So I'll have to do those exercise sessions from there because I can't use the MATLAB here. Well, doesn't matter. Well, it's inconvenience, but I didn't double check that with I just thought that installing MATLAB would be enough, but I'll see. I'll fix that by tomorrow. So, no demonstration of how to use that today. That'll be